Okay, we're going to talk about resonance structures and curved arrows. Um, some important things about resonance. We're not really talking about electrons moving. What we're talking about is the fact that a single Lewis structure, or one structure, is just not adequate to fully represent the bonding. So we're talking about electrons that are delocalized. The actual molecule is the average of the resonance structures. The rules are pretty simple. First of all, a curved arrow has a tail. That's the part without the barbs, and a head. That's the part with the barbs. The tail always has to begin on a pair of electrons. Now, a pair of electrons is either a bond or a lone pair. For resonance, we're talking pi bonds only. Okay? If you're breaking sigma bonds, then you're doing reaction mechanisms. The head, on the other hand, this is where the curved arrow ends. It either has to end on an atom or a bond. You can think of the tail as where the electrons start out, and the head is where the electrons end. But again, in resonance, the electrons aren't actually moving. So there are patterns in resonance, and it's really helpful to recognize them. First of all, let's introduce some terminology. If you have a double bond, the atoms that participate in the double bond are called vinylic positions. An atom that is adjacent to the vinylic is called allylic. There are a couple of patterns associated with the allylic position. The first is the allylic carbocation. So, look over here. Here is a molecule with a carbocation in the allylic position. We can start our curved arrow on the double bond and end it on the adjacent single bond. That gives us this resonance structure. Now, you can't just move double bonds unless there is a carbocation in the allylic position, because that carbocation only has 3 bonds. If you tried to do it with a neutral carbon, it wouldn't work, because that carbon already has 2 hydrogens, which aren't shown. If we did that, we would exceed the octet. A carbon with 5 bonds, that's a no-no. Another pattern associated with the allylic position is the allylic lone pair. So here I've got a nitrogen in the allylic position. The nitrogen has a lone pair. I draw my curved arrow. And if I do it just like that, it's not enough, because I'll have put 5 bonds on that carbon. So I need another curved arrow. And my resulting resonance structure looks like this. So notice I've created some formal charge here. This nitrogen went from neutral to positive, and the carbon went from neutral to negative. Of these two resonance structures, the one on the left is a more important contributor because neutral is better than charged. More stable, that is. Remember, non-zero formal charges destabilize a structure. Here's another pattern that you see. When you have two atoms with different electronegativities, such as a carbon and a nitrogen or a carbon and an oxygen, and they share a pi bond, you can have the pi bond become a lone pair on the more electronegative atom. So here we'll deal with the nitrogen first. There's our curved arrow. The resonance structure we would get looks like this. Now we have a negative charge on the nitrogen and a positive charge on the carbon. So, looking at the oxygen, we can do the same thing. Curved arrow, starting on the pi bond, ending on the more electronegative atom, yielding the following resonance structure. With a negative charge on the oxygen, and is there anything missing here? Oh yeah, a positive charge on the carbon. Again, the neutral structure is more important. When you have a lone pair on an atom that is adjacent to a carbocation, you can change it into a pi bond. That'll complete the octet on the carbocation. So start your curved arrow on the lone pair, end it on the sigma bond that's connected to the carbocation. Your resulting resonance structure looks like this. So now the carbocation is neutral, but now the nitrogen, instead of having a neutral bonding environment, 3 bonds and a lone pair, has 4 bonds. So the nitrogen is positive. Note, in all of these cases, overall charge is conserved. There are also a couple of things you should remember, like never exceed the octet for carbon, nitrogen, oxygen, fluorine. Remember to conserve charge. When you're working in Wiley Plus, draw the lone pairs first. Finally, try to make a resonance structure using as few curved arrows as possible. That way you'll see all the possible resonance structures. For instance, in this molecule here, you've got a pi bond between two atoms of different electronegativity, which gives you now you have another pattern, which is an allylic carbocation.